Hello and good day, learners. I am Kea Sacapaño, and for this lesson, we will be discussing about the cipher methods in cryptography. So here are the common cipher methods, namely the shift cipher or Caesar cipher, transposition cipher, Vigenère cipher, affine cipher, Pigpen cipher, substitution cipher, Francis Bacon cipher, columnar transposition, Polybius square, and the QWERTY code. So for this discussion, we will only be tackling these 5 ciphers. But no worries, the details and application method of the other ciphers can be found in the description below this video. So first up, we have the Caesar cipher, sometimes known as the shift cipher, which is a simple example of a substitution cipher. So each letter is replaced with a letter from a specified number of positions further in the alphabet in this process. For example, if we apply a shift of 3, the letter A would be substituted with D, which is 3 letters later in the alphabet. So this is how the entire mapping would look like. This is the original letters from A to Z, which will then be mapped to starting from D and ending with C. Let us have this next example. So if we apply a shift of 5, the letter A would be substituted with E, which is 5 letters later in the alphabet. And this is how the entire mapping would look like. So again, we have the original letters from A to Z, mapping to letters F to E. So let us suppose that you were tasked to decrypt the message WIRH QSRIC, which was encrypted using a shift cipher with a shift that is equal to 4, mapping from A to Z. Basing from the message, we will use the mapped letters and substitute them to the original one. So W maps out to S, I maps out to E, R maps out to N, H maps out to D, Q maps out to M, S maps out to O, R maps out to again N, I maps out to E, and C maps out to Y, where we will then generate the message send money from the substitution. Next is a transposition cipher. For this method, the letters are just moved around, where each letter retains its identity but changes its position. So let us take this for example. We have the word don't stop me, where we are able to reverse the order in the letters, and we are also able to reverse the letters of each word but not the order of how the words were written. So another mode of the transposition cipher is known as the rail fence encoding. Let us suppose that you use the rail fence encoding with the key that is equal to 3, and your word again is don't stop me. So as you can see from the illustrated example, there are 3 rows since the given key was 3, where the letters are written downward and upward sloping alternately until you finish the whole word, where we will then generate the encoded message from each row, which is DSM, OTTPE, and NO. Next is the Pigpen cipher. The Pigpen cipher structure is based on the arrangement of an alphabet into a series of grids. The Masonic cipher follows the illustrated principle despite the fact that there are various versions of the cipher. The alphabet's 26 letters are arranged into 2 tic-tac-toe grids and 2 diagonal variations of the grid. Because each pair of grids is identical in shape and form, one of each pair is distinguished by the placement of dots with each cell of that grid. This results in 4 differing grids with 1 letter in each individual cell. 1 tic-tac-toe grid with dots, 1 without, 1 diagonal grid with dots, and another without. Because the grids represent pigpens or tic-tac-toe grids, the cipher is more commonly and creatively referred to as the Pigpen cipher or the tic-tac-toe cipher. The cipher is employed by representing each plain text letter with the cell surrounding it, resulting in a message encoded by a series of varying, though similar, geometrical shapes as shown below. Let us take this example and suppose that you were tasked to decrypt this encrypted message using the Pigpen cipher. So let's see. The first one symbolizes the letter I, the next one symbolizes the letter W, the next one symbolizes letter I, the next one symbolizes the letter L, the next one is still letter L, the next one is B, and the next one is E. Now I want you to pause this video and do the remaining ones left, and continue playing it once you have generated the whole encrypted message. If you have done it correctly, you should be able to decrypt the message and generate the word I will be home for Christmas. Have you done it correctly? Before continuing with this part of the video, I suggest that you first read the description below about the Vigenère cipher, and after doing so, kindly play this video again. So I hope you took the time to read about the Vigenère cipher. So in this segment, I will be introducing you to the method of encrypting and decrypting using the Vigenère cipher method, which is done through a table called tabula recta. So let us begin. So let us suppose that we were tasked to encrypt the message get out using the given keyword quick. With the use of the letters A to Z mapping the numbers 0 to 25, let us encrypt this message using this table. So first we have to write the plain text GETOUT. After this, we will proceed to the second row, which is X. In this row of x, we will be substituting the plain text according to their corresponding number. So for G, we have 6. For E, we have 4. For D, we have 19. For O, we have 14. For U, we have 20. And for T, we have 19. So for our key stream, we will be inputting the corresponding numbers of the given keyword, which in this case is the word quick. So Q corresponds to 16, U to 20, I to 8, C to 2, and K to 10. We will then input our keyword's key stream, which are the corresponding numbers in the following columns. So we have 16, 20, 8, 2, 10. And since we only have 5 numbers for our key stream, we will repeat the numbers to fill in the next row, so this next one will have 16 again. Now to get the E sub k of x, or the number to correspond to the ciphertext, we will simply be adding x to our key stream. So x plus 16 is 22, 4 plus 20 is 24. So let us keep in mind that the sum should be less than or equal to 25, since the numbers that correspond to the letters is only from 0 to 25. In this case, we have 19 plus 8, which is equal to 27. So what we'll be doing is to count from 25 to 27, but go back to the first letter to continue counting. So we have 25, 26, and 27, which corresponds to 1. So we will have our T correspond to 1. Remember to do this method only when your sum goes beyond 25. So we will proceed to add x in the key stream for the next column. After doing so, we will simply substitute the numbers to their corresponding letters. So first is 22, which substitutes to the letter W, 24 Y, 1 to the letter B, 16 to letter Q, 4 to E, and 9 to J. So we then generate the encrypted message WYBQEJ for our plain text get out. Now that we have learned to encrypt our plain text, we must also learn how to go back or decrypt a ciphertext. We will still be using the tabula recta to decrypt the ciphertext, but this time writing Y as we are decrypting for the message. So again, we will write the ciphertext and substitute it to its corresponding number to be put to the row of Y and apply the same key stream. Earlier, we had to add X at the key stream to get the corresponding number of the ciphertext, but this time, we will be subtracting Y and the key stream to get the number corresponding to the letters for the plain text. So we have 22 minus 16, which is equal to 6, 24 minus 20, which is equal to 4, and for our 1 minus 8, we will not be subtracting this since its difference would be a negative number. Instead, we will again be basing from our mapped out letters with their corresponding numbers. So since our Y is 1, we will start counting from 1, but this time we count in reverse. So we have 1, 2, 3, 4, 5, 6, 7, 8, where we will get 19. Now we will continue to fill the next columns for this row, and after doing so, we will then again substitute the number to its corresponding letter. And by doing so, we will then generate the plain text. So for 6, we have G, for 4, we have E, for 19, we have T, for 14, we have O, for 20, we have U, and for 19, again, we have T. We will then generate the plain text get out. So we have done the decrypting correctly as it has led us back to the plain text. Now for the affine cipher method. Again, before continuing with this part of the video, I suggest that you first read the description below about the affine cipher, and after doing so, kindly play this video again. So I hope you took the time to read about the affine cipher. So in this segment, I will be introducing you to the method of encrypting and decrypting using the affine cipher method, which is done through the same table as the Vigenère cipher called the tabula recta. So let us begin. So the key for the affine cipher consists of 2 numbers. We'll call them A and B. So the following discussion assumes the use of a 26-character alphabet where M is equal to 26. So A should be chosen to be relatively prime to M, like A should have no factors in common with M. So it uses modular arithmetic to transform the integer that each plain text letter corresponds to into another integer that corresponds to a ciphertext letter, which is the same as what we did to the Vigenère cipher. So the encryption function for a single letter is E of x is equal to AX plus B modulo M. So let us suppose that we were tasked to encrypt the message BOUND, or bound, with the key or K of 7 and 3, with the use of the letters A to Z mapping the numbers 0 to 25. So let us first substitute our formula for our encrypting process. So we have E sub k of x, which is equal to our A is 7, so 7x, plus our B, which is 3, modulo M. For M, we have 26. So we have 7x plus 3 modulo 26. Let us now encrypt this message using this table. So similar to the Vigenère cipher, we will first have to write the plain text. After this, we will proceed to the second row, which is X, and in this row, we will be substituting the plain text according to their corresponding number. So for B, we have 1, O, we have 14, for U, we have 20, for N, we have 13, and for D, we have 3. Now to get our E sub k of x for the next row, we will be using the formula which is 7x plus 3 modulo 26. After doing so, we will then get 10 modulo 26, which will be inputted in the table. So we will be doing the same for the next column in this row. So keep in mind that the number from the formula should still be less than or equal to 25, since the numbers that correspond to the letters are only from 0 to 25. So what we will do to minimize this number and only get numbers ranging from 0 to 25 is that we will need to divide the sum from the formula. So we have 101 divided by 26 is equal to 3.88. We will then multiply 26 to the quotient, but we will only make use of the whole number, so it will only be 26 times 3, which will then be equal to 78. Now we will be subtracting 101 from 78 to get the difference of 23 modulo 26. Remember, we only do this method if the sum from the formula goes more than 25. We will then repeat these steps to get the answers for this row in the next columns, and you should be able to get these results. After doing so, we will again substitute the numbers into the letters A to Z and generate the ciphertext for each letter. So for B, we have 10 modulo 26. 10 substitutes to the letter K. For the next one, we have 23, which substitutes to the letter X. For the next one, we have 13, which substitutes to the letter N. For the next one, we have 16, which substitutes to the letter Q. And for the next one, we have 24, which substitutes to the letter Y. So we will have our ciphertext for bound as KXNQY. So now that we have learned how to encrypt the message using the affine cipher, we will now proceed to decrypt it using the same method. In deciphering the ciphertext, we must perform the opposite or inverse functions on the ciphertext to retrieve the plain text. The decryption function is d of y is equal to a raised to the power of -1 multiplied by y minus b modulo m. So let us suppose we were to decrypt the ciphertext, which is KXNQY, using the same key, which is K of 7 and 3. I am sorry, I seem to have mistakenly written 13. Please take note that our K is 7 and 3. So let us first substitute our formula for our decrypting process. So we will be basing from this table here for the substitution of a raised to the power of -1. So let us find 7 in A's row, and here 7 corresponds to 15 as it's a raised to the power of -1. So let us now substitute the formula to get d sub k of y, which is equal to 15, and y minus our b, which is 3, and then modulo m, our m is equal to 26, so modulo 26. Now, once again, the first step in the table is to convert each of the ciphertext letters into their integer values. After doing so, we will get the d sub k of y using the formula. For the first column, we have the product of 105 modulo 26. Again, keep in mind that the product from the formula should still be less than or equal to 25, since the numbers that correspond to the letters are only from 0 to 25. 105 exceeds 25, so as what we have previously done, we will be minimizing this number by dividing 105 to 26, which will then be equal to 4.03. You will then multiply 26 to 4, only using the whole number and excluding its decimal point, which will then be equal to 104. Finally, we will be subtracting 105 from 104 to get the difference of 1. So we have 1 modulo 26. Again, remember, we only do this method if the product from the formula goes more than 25. So we will repeat these steps to get the answers for this row in the next columns, and you should be able to get these results. Your letter K should be 1 modulo 26. Your letter X should be 14 modulo 26. Your N should be 20 modulo 26. Your Q should be 13 modulo 26. And your Y should be 3 modulo 26. And after getting this, we will then again substitute the numbers into the letters A to Z and generate the plain text for each letter. So for K, we have 1 modulo 26. 1 substitutes to the letter B. For the next one, we have 14 modulo 26, which substitutes to the letter O. For the next one, we have 20 modulo 26, which substitutes to the letter U. For 13 modulo 26, we have N, and for 3 modulo 26, we have D. So we will have our ciphertext KXNQY to be back to the plain text, which is the word bound.